Okay, so welcome back to Common Core Algebra II. Today's lesson is 4.5, the method of common bases. I kind of like these. These are like my favorite things to do, so hopefully you enjoy them as much as I do. So there are very few algebraic techniques that do not involve technology to solve equations that contain these exponential expressions. So we're going to look at one of these techniques called the method of common bases. So in exercise 1, it says solve each of the following simple exponential equations by writing each side of the equation using a common base. So what you need to determine here is most of the time it's pretty obvious, but you need to bring it down to a base that's common to both of them. In other words, when I look at A, I can see that I have 2 to the x on the left-hand side, and on the right-hand side I have 16, which I can rewrite in base 2. Because I know 16 is 2 times 2 is 4 times 2 is 8 times 2 is 16. So I know that 2 to the 4th power is equal to 16. And as soon as I have those same bases, I know my exponents have to be equal. All right? So keeping that in mind, it's the same situation in letter B. I have 3 to the x on the left-hand side, and I can rewrite my 27 in a base 3. So I know 3 to the 3rd power is 27. So I know as soon as I have those same 3's, those bases, I know my exponents, again, need to be equal. Don't flip out with the F word over here, because now we have fractions. So here I have 5 to the x, and I'm going to remind you that 1 over 25 is the same thing as 5 squared, but it's 5 to the negative 2, which brings that back up into the denominator, or in this case, it brings it down into the denominator. All right, so here x is equal to negative 2. And this is just flipped around. This isn't a big deal. I know that 16 is the square of 4. So I know that 16 can be written as 4 squared. And I usually put that then inside the parentheses, and the x goes on the outside, equals 4 to the 1st power. As soon as I have my bases that are the same, I have my exponents. I know 2 times x is equal to 1. And now you need just some simple algebra to solve this for x. X is equal to 1/2. If you're a decimal person, you can say x is equal to 0.5. It's the same thing. And that makes sense, right? Because we can go back and check this. 16 to the 1/2 power is the same thing as the square root of 16, which is equal to 4. Write down what you need to and meet me at exercise 2. So in each of these cases, even the last more challenging one, we could manipulate the right-hand side of the equation so that it shared the same common base with the left-hand side of the equation. We can exploit this fact by manipulating both sides so that they have a common base. First, though, we need to review the laws of exponents, all right? Because this is what we were talking about the last time on that last problem. When you have 3 raised to the x, that's the same thing as saying 2 to the 3x. When you have 3 raised to the 2nd power raised to the 4x, this is 3 to the 2 times 4x, or of course we could rewrite it as 3 to the 8x. This is going to be 5 to the negative 1, 3x minus 7, but we're always going to simplify it to negative 3x plus 7. And the same thing here goes 4 to the negative 3, 1 minus x squared, and we're going to simplify it just a little bit to the negative 3 plus 3x squared. Nothing very challenging there. I think that you understand that pretty well. Again, when you have questions, you should be putting little notes in your margins and making sure that it is addressed tomorrow when you come back into class. So write down what you need to, and then we'll move on to exercise 3. Okay, this is where it starts getting fun. So in exercise 3, you can see how we have 8 and we have 32. Now 32 is not a base. You're not going to be able to bring that down to base 8, because 8 times 8 is 64, and it's not 32. But hopefully you realize that 8 and 32 are both powers of 2. All right, so we can rewrite 8 as 2. 2 times 2 is 4 times 2 is 8. So we can rewrite this as 2 to the 3rd power but don't forget about the x that sits right here. All right, equals, and the same thing with the 32. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 32 is 2 to the 5th power. All right, so now once you have the same base, you know the exponents have to be equal. And don't worry that it's a fraction. Many times it will be, because if it wasn't a fraction, it would be easy to solve. All right, why don't you give B and C a try on your own? See if you can figure it out. Well, hopefully you realize that 9 is a power of 3, and that's 3 squared to the 2x plus 1. And 27 is the same thing as 3 cubed. All right, so then your same base, so your exponents, 2x plus 1 is equal to 3, 4x plus 2 is equal to 3, minus 2 from both sides, and x is equal to 1/4. I skipped a few steps there, so please make sure that you're understanding what those steps were. C is a little complicated. As soon as you see that fraction, people start to flip out a little bit. But 125 is the same thing as 5 cubed to the x power is equal to, and 1 over 25 is 5 to the negative 2 to the 4 minus x. So you get 3x is equal to negative 2 times 4 minus x, and simplify it. 3x is equal to negative 8 plus 2x. We're going to bring this 2x over to the left-hand side, minus 2x from both sides, and you get x is equal to negative 8. Okay, so write down what you need to before we move on to exercise 4. Exercise 4 is not that much more difficult than what we've been doing, but it does require a little bit of a quadratic in here. So in this case, 2 is our base, to the x squared minus 3. And can we rewrite 64 in a base 2? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. 1, 2, 3, 4, 5, 6. So 2 to the 6th power. So as soon as you get those bases, now you know that x squared minus 3 equals 6. Add 3 to both sides. Very nice. We get x squared is equal to 9. Now please beware, because at this point you can ask yourself, what number multiplied by itself gives you positive 9? And the answer is positive 3, but it's also negative 3, because a negative times a negative is a positive. So please make sure that when you are solving this, you don't pick number 2 by accident. Okay, so this technique can be used in any situation where all bases involved can be written with a common base. All right, so now what we're doing is we're going to look at a little bit more complicated problem, more challenging problem. And I'm going to remind you that sometimes, even though these look challenging, step by step, they're not bad. So please make sure you're not just looking at this and freaking out. So they give us 2 exponential curves. All right, so take a deep breath. Not so bad. Here's one. Here's the other. All right, and they intersect at point A. So here's the point A right here. A rectangle has one vertex at the origin, which is down here, and the other one at that point A. All right, and we want to find its area. So let's answer question by question, because this is not that bad, folks. Fundamentally, what do you need to know about a rectangle to find its area? Okay, not so bad. I can do this. So the area of a rectangle, let's see, can we go back to that 4th grade, is length times width. Okay, so if we consider this the length and this the width, that's all we need to know. So you answered that one. Hopefully that wasn't so rough. How would knowing the coordinates of point A help us find this area? So hopefully you say to yourself, well, this point A is going to be a point x comma y. So that x is going to represent the distance from here to here, right? Look at that. That's going to be my length. So that's going to be, and beware, because x is actually going to be a negative number because it's to the left of the y-axis. So I'm going to represent that with the absolute value of y. And I'm sorry, the absolute value of x. And the y is going to represent the distance from down here to up here. And this is going to be our y. Now, y is going to be positive, but just to make sure, we're going to call that one the absolute value of y. So we can write that down. The length is going to equal the absolute value of x, and the width is going to equal the absolute value of y. Now, can they be switched? Can you let the width be the absolute value of x? Absolutely. Okay, so as long as you're consistent with length and width, one being x, one being y, we're good. So we did that one. Now it says find the area of the rectangle using the method of common bases. So if we're looking for where these two intersect, because that's what we're doing here, we're going to take the first one. I just have to slide up so I can write it down. We're going to take the first one, which is 4 raised to the x plus 5 over 2, and we're going to set it equal to 1/2 raised to the 2x plus 1. We'll slide up here. I'm also going to move it over a little bit. Will it let me move it over? Wrong one. Yes. Okay, so here we have this moved over. So let's get those common bases. So hopefully, one step at a time, the 4 is 2 squared times x to the, raised to the x plus 5 over 2. And 1/2 is going to be 2 to the negative 1 to the 2x plus 1. All right, so as soon as we get those common bases, we know that 2x plus 5 over 2 is equal to negative 1 times 2x plus 1. You're going to see this is not difficult to do. Make sure you can use your calculator if you need to. So when we distribute that 2, this becomes 2x plus 5 is equal to negative 2x minus 1. We're going to bring this over to this side, and we're going to get 4x, so add 2x. 4x plus 5 is equal to negative 1 minus 5 from both sides. And we get, I'm going to just bring it over here if that's okay. Bring it up here. And I get 4x is equal to negative 6. Divide by 4. And x is equal to, now we need to reduce that negative 6 over 4 to negative 3 over 2. Always, always make sure that you are reducing. Now that's our x, and the way we find our y is use one of our equations. It doesn't matter which one we use. So we can say y is equal to 1/2 raised to the 2 times negative 3 over 2, our x, plus 1. So y turns out to be 1/2 raised to the, let's see, 2 times negative is going to be negative 3 plus 1, which is 1/2 raised to the negative 2 power, which is equal to 4. So my y is equal to 4, and my x is equal to negative 3 over 2. Now make sure you're answering the question when you're all said and done, because the area is equal to the absolute value of 3 over 2 times the absolute value of 4. So when you add those two together, when you multiply those two together, you get positive 6 square units. So make sure when you're all said and done, there are lots of different pieces to that one. So just keep in mind what you're trying to find, your x and your y, and then multiply them together when you're all said and done. So write down what you need to, and why don't you try number 6 on your own? I'm going to slide up in a minute, and that way I want you to try it first before we tackle it together. Okay, so at what x-coordinate will the graph of y equals 25 x minus a intersect the graph of y equals 1 over 25 raised to the 3x plus 1. So again, we're going to set these two equal to each other. So x minus a is equal to 1 over 25, 3x plus 1. The bell's going to ring, so I'm going to run through this pretty quickly. Base 5, this base squared, x minus a is equal to, I'm sorry, it's 125. So this is going to be 5 to the negative 3 raised to the 3x plus 1. And now simply set them equal. So 2x minus a is equal to negative 3, 3x plus 1. 2x minus 2a is equal to negative 9x minus 3. Bring the x over, add 9x to both sides. I'm going to slide this down so I can get a little bit more room here. And I get 11x minus 2a is equal to negative 3. Add 2a to both sides, reminding ourselves that we cannot combine these two. So you get negative 3 plus 2a and divide by 11. So there's our answer. I know I did that really fast. You might want to pause it, go over it again, make sure you're understanding it. And until next time, tomorrow we are going to make sure that we're going over the classwork. If you have any questions, please make sure you're bringing them in to me tomorrow so we can spend some time going over them. There's the bell. Perfect timing. Go back, make good choices, and I'll see you tomorrow, kids. Bye-bye.